This video shows how to get started with Xilinx Zynq SoCs. Before starting, DG-Lent drivers and Xilinx Vivado and Vita software tools shall be installed. PCAP drivers shall be installed for Ethernet communication. CASP board support package for Xilinx FPGAs shall also be installed. Please refer to our earlier tutorial videos on how to install board support package and get started with FPGAs. In this video we use DG-Lent RT Z720 FPGA board. We start by using existing template project available in board support package installed directory. Copy the template project to your preferable location. Open the two projects located in the template directory. One project is for programmable logic and the other is for processing system of the SoC. Also open the Vivado project located in the template directory. We use the shared memory 0 of the FPGA COM block for communication between the processing logic and processing system of the SoC. This shared memory is visible as SHM0_port A of the CASP/HLSIP. Through some VRAM and AXI interface blocks, the SHM0_port A is further mapped to master AXI GP0 memory address space of the Zynq processing system. The master AXI GP1 address space of the processing system is directly mapped to drive some LEDs and take some digital inputs and an ADC input in the programmable logic. Please go through the project documentation for further details. Modify the model to include basic data acquisition and control functionalities. We use one digital signal from onboard switch 0 and one analog signal from onboard ADC 0 for data acquisition. We control the brightness of an onboard tricolor LED with 3 PWM signals. Click on Run button to build the model. CASP uses Xilinx Vitis HLS tool to compile the model and convert to respective Verilog IP. After compilation, check for any generated errors. User is also recommended to go through the generated log file for any errors. In Vivado, open the IP catalog and delete the existing CASP/HLSIP repository path. After removing the path, update the IP from other repositories. For this, click on Report IP Status and then upgrade selected buttons to update the IP. After updating the IP, check whether all the input and output signals from the IP block are connected to respective board pins. Connect a dummy constant output block to the open inputs of the PWM blocks. Click on Generate Bit Stream to generate Start FPGA design flow and generate bit stream file. This operation may take several minutes to complete. After completion, the generated bit stream file is available in the path shown in the video. Now, let's move on to the processing system part of Zynq SoC. The processing system model consists of logic to control LEDs through the programmable logic. The communication part consists of shared memory FIFO block and LWIP block connected back to back. The address of shared memory shall be same as the address of the FPGA COM block from the programmable logic model. All other parameters shall be matched between the FIFO block in the processing system and FPGA COM in the programmable logic. The LWIP block data send and receive parameters shall be matched with the FIFO block. UDP protocol is used with suitable IP and port addresses. The logic part consists of analog blink logic that is mapped to LED 3 pin through master AXI GP1 memory address space. The push button logic consists of varying the blink frequency of LED 1 and LED 2 based on the push buttons pressed. Insert a suitable memory card in the host PC before building the model. Delete the existing boot.bin file from the memory card if present. Enter the drive letter of the memory card in the programmer port parameter. This will enable CASP to copy the generated boot.bin file to the memory card automatically. Click Run button to build the model. This will create a boot.bin which consists of processing system's ELF file and the programmable logic bit stream file. The boot.bin file will be automatically copied to memory card if no errors occur. Remove the memory card from the host PC and insert it into the FPGA SD card slot. Set the onboard jumper JP4 to SD mode and press reset button. The board should restart and load the program from SD card. Now check the working of Ethernet communication. Sensor value seems changing with respect to the light intensity. This means that the data transfer from programmable logic to the processing system and further to the host PC is working as expected. Push button logic is also working as expected. Toggling of the switch can be seen in the configuration window. Now, we quickly create a native project to plot the sensor data and manually control the tricolor LEDs. These steps are already demonstrated in our earlier videos. Configure suitable simulation settings to run in real time. Also, configure the simulation panel to include a plotter window and a control window. Start creating the model. Configure the communication I/O to include the UDP endpoint representing the target. Click the Run button to compile the model and start simulation. Simulation seems working as expected. Thank you for watching this video.